We are in section 1.5, Elements of System-Level Troubleshooting. The ability to diagnose and correct is an important part of having a career in computer technology or electronics in general. We're going to be looking at some of the strategies used in troubleshooting, and these strategies include block diagram thinking, signal tracing, signal injection, diagnostic software, observation, and substitution. The first one we'll look at is block diagram thinking. And troubleshooting complex electronic systems can be an overwhelming task. Many systems are too complex to be able to visualize all of the system details. One way to avoid being overwhelmed is to logically troubleshoot the system from a block diagram perspective. And earlier in this chapter we had looked at block diagrams, and we had observed that block diagrams just gave us the big picture of a system and didn't give us the detail. And this is often helpful when trying to diagnose a problem in a large system, because you don't want all that much detail. You actually get lost in the details, so you want a bigger picture, which a block diagram can provide. The next troubleshooting technique we'll mention is signal tracing. Signal tracing. It's a technique that involves monitoring circuit quantities at various points throughout the circuit. At each point, you evaluate whether the measurement is good or bad with respect to the correct or measured value. Typically, oscilloscopes or voltmeters are used to do this, and one of the important or necessary skills in this is that you actually know what is the value that should be measured at given points. And usually with given systems you'll have technical manuals or schematics that will provide that information. By tracing the signal through the system, particularly sequential systems, you will reach a point where the signal is no longer what it should be. And at that point you determine, well, this is probably where the fault is. One way to implement signal tracing is called divide and conquer. And in this strategy, measurements are made at the middle of the system. And I guess if I can draw a very basic, let's just pretend that here we have a given system and a signal comes in here and the signal comes out over here. And let's pretend that we have test points throughout this circuit, and we can go in and we could measure every single one of these test points to determine when does the system fail. Or we could just go in and say, well, let's measure right here, and we make a determination, is that a good signal or is it a bad signal? And again, you have to be familiar enough with the system to determine, is that a good signal or is it a bad? Well, if it's a good signal, then you know the problem is over here, so you'd probably divide and conquer again and make a determination, and is it here or is it here? And so that's the concept of divide and conquer utilizing signal tracing. Then diagnostic software. Diagnostic software is a powerful tool in the troubleshooting endeavor. This specially designed software requires only limited system capability in order to execute successfully. Diagnostic software is common in troubleshooting notice for computer systems, memory, and hardware errors. And a couple of the diagnostic software programs I'm familiar with are Norton Utilities, SciSoft Sandra. In fact, SciSoft Sandra, you can get it as a free download, and it's an interesting program that you're using it to diagnose computer system faults. Diagnostic software-based systems are also used in automotive troubleshooting. Observation. The most important tool in your troubleshooting toolkit is the power of observation. And when we say observation, this is all of the senses. You can see, but you can also smell, and you can also hear. And oftentimes in diagnosing electronic systems, it isn't just what you see. Sometimes it's what you smell that tells you a lot. Those of you that have been around this business know that there's just that smell of burning components that tells you something is very wrong. Sometimes even you'll hear sounds that shouldn't be there. But anyway, observation is very important in diagnosing faults. Many defects can be diagnosed simply by carefully observing the operation of a circuit. Observation extends to 3 other important troubleshooting strategies. Besides specific observing, there is the user interview. And here, what has the user observed about the circuit? Then there's a concept I hadn't heard. This particular term, front panel milking, is not one that I had heard of before, but this is the way your text describes it. And what it is the intentional operation of all of the front panel controls while observing the behavior of the system. And this just simply means that you're putting a given system through all of its paces and adjusting it and doing all the things that this system should be able to do and observing its operation. And again, this is only going to be helpful if you know how that system is supposed to operate. If you know how it's supposed to operate and then you notice something that's not quite right, as a technician you'll be able to pick that up. But if you do not know the correct operation of a given system, this may or may not help. Then review of history using logbooks. Logbooks can be of great value if they are maintained. Oftentimes, if a group of technicians maintains logs of the systems they're troubleshooting, oftentimes they can diagnose weaknesses in the system, and then when it comes to a fault that comes up, they can look in their logbooks and say, oh, that particular fault has been occurring frequently, and rather than do that, they can just go directly to the fault based on documentation. Substitution, benefits and risks. And well, let's first, what is substitution? Once localized, the suspected component can be substituted and the circuit evaluated again to verify the component operation. Well, substitution. Well, let's pretend that here we've got a let's just pretend this is a radio. And we'll pretend that this is here we've got a radio here, and this one is bad, it doesn't work. And so here we have another radio, and this one is good. And this is the technician has this available, and so this radio has come in and he's supposed to repair it. Now, typically, when we're talking about this is probably a communication system, maybe a communication systems for an aircraft or something. It's probably a high-end device. And most radios are going to have, and I'll draw some lines here, and we'll pretend that these are the circuit cards or modules within this bad radio. Now, in the substitution method of troubleshooting, what the technician would do is that he would simply pull out, here we have circuit card 1, and he would take out circuit card 1 and replace it. And if that fixed it, he knows that. But typically, you would replace several before you got to the one that was the faulty one. Now, let's pretend, just for sake of discussion, we'll pretend that he determines that circuit card number 4 was the faulty component, and so he would probably go over to his supply system and he would order circuit card number 4. He would put it into the radio, and the radio is fixed. And this is the concept of troubleshooting by the method of substitution when you have a group of known good components. Substitution can be used at nearly any level in system integration. In aviation, when a system fails, the entire system is often removed and replaced. And so we're going to look at in aviation as an example. We talked about that box in the previous screen. Let's pretend that in this particular aircraft the radio system has failed. The pilot can't talk to ground, and he just landed, and he's got to take off soon, and he can't wait for technicians to fix this thing. So what they would do is they would just, and this would be major substitution, they would just take this entire black box out and take a known good black box, plug it in, and the radio works, and the pilot flies away. Well, the bad box now is going to go down to the folks in maintenance, and the technicians are going to have to fix this thing. So the technicians take the black box apart, remove and replace modules until the box is fixed. And so they would be doing the process that we had looked at over here, substituting modules until they repair the box. When repaired, the radio goes back to the supply system until it's needed by another aircraft. So in this case, this box, now that it's fixed, it goes into the supply system, and it waits until another radio fails, and then it's plugged into an aircraft, and away it goes. In this particular cycle here, the defective modules are then repaired by the maintenance personnel, and this would typically involve going down to the component level and repairing the faulty circuit card. And there's no substitution here, but in these two upper levels of the maintenance cycle, substitution is a very viable way of repairing systems. Substitution is not always practical as the primary method of troubleshooting, as it requires, notice, a tremendous inventory of spare parts in complex systems. Now, in the aviation industry, there's lots of revenues there, and there is just a need to be able to make aircraft go immediately, and so typically the supply systems will be able to support that. But in smaller systems, that probably isn't always that type of inventory wouldn't always be available. So in that case, substitution will not always be a viable alternative. Occasionally, and this is another problem with substitution, occasionally system chassis will short, damaging connected modules. And as known good modules are plugged into the system, it destroys them as well. And I'm just thinking of an example. For example, most cars today have an onboard computer, and occasionally the onboard computer will fail. And so the technician goes down and thinks, oh, the onboard computer failed, I'll just replace it. So he replaces it, only to have the one he replaced go up in smoke as well. Well, the problem probably is that there is something in the chassis of that vehicle that is shorting out the onboard computer, and so that the original problem wasn't the onboard computer, it was a short in the chassis connected to the onboard computer, and so now he's got two broken computers. So substitution doesn't always work, and it requires experience and good judgment on the part of the technician to be able to determine when substitution is going to work and when it is not going to work. So this is, we have in section 1.5, we've addressed the elements of system level troubleshooting, and we looked at substitution. We have looked at observation. Remember, your senses can tell you a lot about troubleshooting. We've looked at diagnostic software used primarily in compute, but it is used also in the automotive industry. Lots of industries now use diagnostic software to troubleshoot electronic systems. Signal tracing, block diagram thinking. So that concludes elements of system level troubleshooting, section 1.5.